remembering that. Okay, it's time to start. The people that I have as not here are Amanda, Austin, and Edward, and there's James. So, yeah, no. All right, let's get going. Oh, I do need to start this. I hate it when I forget that. Okay, we're going to talk about energy again today. Hopefully you learned a fair amount about energy in lab yesterday, as well as from the first lecture on work. So today maybe some review, although it's likely there's plenty to learn still. You doubt that? You got it all down. Okay, that was... No, that's not what I meant. I doubt that LGM review. Oh, okay. So, let's get into looking at energy and start with a clicker question that you had last class. Oh my goodness. Can't answer yet because I forgot to hit the thing to start the presentation. Okay, now you can answer. So which figures illustrate, notice I changed the wording so it would be more precise, the work done on the briefcase/lawnmower by the force F indicated. And this is one we have to answer all the correct ones and click enter. Okay, still waiting for Toussaint, Sade, Edward, Sally. Okay, so we had answers were 1, 0, 0, 20, and 21. Okay. Really? That's good, because A is the correct answer. I was like, why did only one person put A? Maybe it's set so it only allows 2. I'm not going to stop it and check that now because that'd be more curiosity. It may be that it only allowed the first 2 that you typed in or something. I'm glad to hear that more people answered A. When we had this question last time, to get the right answers, what was the single question that I polled students about to get the right answers? If there is a distance parallel to the force. So we just look at this and we look at A. While the force is not parallel, it's not perpendicular, so a component of the force is parallel to the distance, so A is definitely doing work. B, there's no distance, so no work. C, there's a distance, but it's perpendicular, so no work. D, just like with A, the force has a component parallel to the distance, so it has work. And E, the force is anti-parallel, which means it's a negative work, but that's still work. Does everybody understand why this one here represents negative? Well, that was really nice. Represents negative work. Okay, one person nodded that she did, and I'm going to assume she speaks for everyone because no one nodded no. If the force is opposite direction of distance moved, it's negative work. Okay, graphical calculation of work. We've already learned with our definitions for motion equations, we had things like the distance was equal to the average velocity multiplied by the change in time. And we said, what we can do then is we can take a graph where we have the velocity and multiply that by the time for each small piece and take the area under the graph, and that gives us the distance traveled. We had that on the test, right? Problem that had you do that, find the area under the graph, basically. So now we're going to take the equation for work force times the distance parallel that it moves. If you look at those equations, you should say, wow, they have the same form. Not the same variables, but the same form. You have something times a delta something. And it turns out, because they have the same form, the exact same thing works. If we make a graph that shows the force as a function of the position, then we can just say, okay, going from here to here, I had this force cosine theta here, because it's saying, well, the component is parallel. Move this distance, so the force times the distance is just the area of that box. And if I had something that wasn't a constant force, I could break it up into a whole bunch of small boxes and just add up the areas for each of those small boxes and have the total work. So just like when we used position from a velocity versus time graph, we can take a force versus displacement graph, and provided the force is the force parallel to the displacement, then the area under that graph will give us the work. So area, total area under the curve equals the total work done. So that takes us to clicker question number 2 right off the bat. Wow, Jaron answered before the question was up. You answered incorrectly, though. How much work is done in stretching this spring, shown in this graph, a distance of 0.8 meters? I drew a box to show you where it is. And approximate that this line here is coming right at the 4. I'll even write the general work equation here for people who... You just want everyone to know that you'd be wrong? Is that what you're saying? Yeah? What's the what? That's the 0.08 meters. Got your answer, Michael in Toussaint? Okay. And the answers are in. 0, 0, 4, 13, 1, 3. Now, this is not the correct answer. So there are 2 roughly even that were left over, and then 3 others that were less common. Talk to the people around you. You don't have to talk to the ladies in front of you or go sideways over to Michael. And talk about what answer you would choose among the remaining ones and why. I don't know.
It's still a force. Yeah, no matter what.
What do you think? It's not. Oh, 0.4. I know. I don't think I have time on this.
So my thought is, in the real world, how often do you have a force?
Let's reopen it.
Huh? I will be. Michael?
What's that 49?
That's actually the equation that fits the line. Okay, let us go ahead and re-pull this thing. And so now answer based on what you learned in your discussion with your classmates.
Wait, did you have to answer a second time?
You have to answer now again. Yes.
Oh, okay.
Jaron went from first to last. Actually, not last because Edward hasn't answered yet either. You have a chance to beat Edward. Nope, you're last. Okay. The answers we got the second time through were somebody changed to 0. I'm not sure why that stopped. Oh, because I'm on lines. 17 people, so we had 13 that changed to that. Thankfully, everybody remembered that was the wrong answer. The one person there moved away, and 3 people stayed with that. Well, now we have a clear majority here in answers. And so let's talk about what could go right and wrong with the answers. First of all, people who answered D the first time. Why would you have answered D? Because we're not good enough. I mean, what were you thinking? You're all good enough, you're smart enough, and doggone people like you. What did you say, Lindsay? Okay, you just looked at force times distance and forgot that the force is changing here instead of a constant force. If it had been a constant force, well, that would have been correct. But with the changing force, unless you're taking a calculus class, the only way you have of doing it is, well, what's your method? Find the area under the curve. So I told you to just approximate that it had a force of 4 newtons up here at the top. So if that's 4 newtons and this is 0 newtons, then the rise was a total of 4 newtons there. The horizontal portion was 0.08 meters. And this makes a triangle for the area under the curve. So what's the equation for the area of a triangle? I heard words, but I did not hear an answer. That is, I didn't hear what the words said. What was the equation for the area of a triangle? 1/2 base times height. So we just took 1/2 of my base, 0.08 meters, multiplied by my height of 4 newtons. And that gave me 1/2 of 0.32, or 0.16 joules. So does everyone understand the methodology there? Understand how the graph works to find work? Because things that I don't like are when people, miss points on a test on something that should have been reasonably simple. If you have this on a test, now it should look simple to you, I hope. All right, moving on. We're on the downward half of my slides. I didn't have many slides prepared today. Here's an example of a box on a conveyor belt, and the box has all of its forces shown. You have an applied force that's pushing it to the right. You have a frictional force because there's some friction in those rollers pushing to the left. You have a work force pushing up, a weight pushing down, and a normal force pushing up. And it's going to move horizontally. Now, of course, you may have had this in your reading quiz. You may have just read it in the textbook, because it comes from the textbook. But when you look at this, one of the important questions you always have to ask is, which force or forces can do work on the box here? And so, I'll start with last in, first out. Austin.
Yes, what force is there acting on?
Can the applied force there do work on the box?
Yeah.
Yes. And why did you say that?
Because there's no friction. Or it's because the
Parallel to?
parallel to displacement.
Okay. The applied force is parallel to the displacement. As we saw in the first clicker question, reiterated, you can only have a work done if you have displacement parallel to the force. And that applied force is parallel to the displacement, so it can do work. Okay? Next in line, Alexis, who clearly understands this concept. What about the weight force?
Is it doing work?
Can it do work? Will it do work in that motion?
I'm going to say no.
Why is your answer no?
Because it's not parallel to displacement. It's kind of perpendicular.
And by not parallel, she meant perpendicular. It's perpendicular to the displacement, hence it can't do any work. Lindsay, what about the normal force?
No, it can't do work.
Because? And Haley, what about the force of friction? Yes, it can because? It's anti-parallel. And because it's anti-parallel, what does that further tell you about the work? It's going to be negative. It's working against it. So now that we've determined which ones can do work, we'll go ahead and calculate the work really quickly. Work is equal to force dot delta x. Remember, why do I always write it force vector sign dot delta x vector sign? Why do I always write it that way? To remind myself that I'm only multiplying the parallel parts. And by the way, this is not the same as this. That would just be a multiplication. If you don't have a vector sign, the dot means multiplied. Now, for the force applied and the force of friction, we would get the same answer, but the force of gravity, the weight, would have given us a non-zero answer if I wrote the equation this way. Right? So this equation, it's incorrect that way. It would have given you something other than 0 because it doesn't take into account directions. So, for the work done by the applied force, force applied times the distance, very quickly, 120 newtons times 0.800 meters is equal to 96. How many significant digits do I have? I have 3, so I need to put 0.0 joules. The work done by the force of friction, minus, because they're anti-parallel, as Haley said, my force of 5.00 newtons times 0.800 meters. Sorry, I ran out of space there. Equals minus 4.00 joules. Notice I do write those trailing zeros because they're significant. Writing them means I know these values are 0. If you don't write them, it means I don't know what that digit is. So we calculated those two works. What's the net work? It's going to be the work done by all of them. So work applied plus the work from gravity plus the work from the normal plus the work from friction. We already specified those two are zeros. And so then I would just put in my 96.0 joules plus my minus 4.00 joules. And when I add those up, I get 92.0 joules. Still 3 significant digits in my answer because the greatest of the least significant digits was in the tenths. And so the least significant digit in my answer is in the tenths, which gives me 3 significant digits.
So if you're asking for work done on the box, would you give the work applied or would you give the final work net?
Hopefully the wording would be more precise. Either the net work on the box or the work done by the applied force or something like that so that it's clear. Because when you just say the work, it could mean different things depending on who's asking and what they're trying to get at. So hopefully, like for test questions, it's going to be more clear. Yes?
So couldn't we have found the net force and just use that in our network?
Yes, we could have also said the work net is equal to the force net dot delta x. And so then I could have added up all the forces to find one force net vector. And in fact, when you go through the derivation for the equation for kinetic energy, that's what you do. You say, well, force net, that's equal to mass times acceleration according to Newton's second law, dot delta x. And then with calculus, you have that's equal to mass times dv I know only some people in class are following this. I moved the dt from under the dv to under the dx. But dx dt is v. And you have to have the summation part that we don't have, which is the integral. Integral of mv dv is what you get for the calculus part. It's really got this here. Okay, so to people with calculus, that makes some sense. Calculus students can see this is why kinetic energy has an equation of 1/2 mv squared. Because we have the work energy relation that says work net is equal to the change in kinetic energy. Remember, kinetic energy, energy in motion. In fact, I think that's my next slide. Kinetic energy is the energy in motion. We'll see if it's the next slide. If it's not, I'll still keep talking. Oh, nope, the next one's potential energy. Well, because I started kinetic energy, and I've said it 3 times, what's kinetic energy? Energy in motion. And we started this section a week ago by identifying that energy is the ability to do work. So we identified right there a relationship between work and energy. And so energy, the ability to do work, that relationship is mathematically shown with what I put, the work net is equal to change in kinetic energy. When you do work on a system, you're going to change its kinetic energy. If you do a net work. So you take that net work, it's going to be force net times the distance it moved, and you can calculate how much kinetic energy is going to change. And then it's just calculus, mathematics, to say that means that the energy in motion must be 1/2 mv squared. So it's not hard math, but it's math that we don't do in an algebra class, to show that the energy in motion is 1/2 mass times speed squared. Now, things to think about. I don't know, you probably don't all watch football like I do. But in football, one of the things that we love is the big collisions. And everybody knows if I have like a 230-pound running back who can run really, really fast, that it's going to really hurt when he hits me. Now, if instead of a 230-pound running back who runs really, really fast, if it was a 150-pound running back running the same speed, would that hurt? Yeah, it still hurt. Would it hurt as much? No. The reason it wouldn't hurt as much is he's not going to do as much work on me. He's not going to transfer as much energy to me when he hits me. Why not? Because kinetic energy is 1/2 mv squared. If instead of 230 pounds, he's only 70 pounds, he's going to carry a significantly smaller amount of kinetic energy, which means he has less energy to transfer to me, to break my bones or whatever. Now, if instead of being a 170-pound person running really fast, it's a 290-pound person that's lumbering along, is it going to be more or less painful to get hit by that 230-pound person lumbering along at a slow speed? Okay, it depends on what lumbering means and the mass, because the equation is 1/2 mv squared. Speed is more important to the kinetic energy than mass. But when you have somebody with a higher mass, if they're going the same speed, they're going to hurt a lot more than if they're going at a slower speed because of that speed squared. Now, I know, I'm pointing up here and there's nothing up here that relates to this. It will be on the next slide, but once I got started, I couldn't stop. So kinetic energy is one form of energy. Energy something has because it's moving. And the way you can always remember kinetic energy has because it's moving is because if I'm running and I hit you, I'm going to do some work on you. I'm going to apply a force and you're going to move. Jerry and I played football in the same field, but I've never hit him, so no one here has the experience. I think I've played with Zach, but yeah. We'll just have to get out there more often, and you guys play line position or something, or try to block me just so we can, I say try. You can be successful. Or... So, potential energy now. Remember, kinetic energy was the first one identified, then potential energy. Potential energy is, once again, the ability to do work, but now it's because of configuration. And we saw that in good manner yesterday. You have gravitational potential energy. This pencil, if I let go, there's a force due to gravity that's going to make it fall, and so gravity didn't work on it. We have the spring potential energy. You take your spring, if you pull it, it will pull back, you let go, and it snaps shut. It was storing an ability to do work because you stretched it or you lifted it. Now, there's something that's very important about potential energy. We do not define potential energy for every force. Only specific forces that we call conservative forces. And the term conservative means that if you do work on it, it will always give you back exactly the same amount of energy that you put into it. So it's conserving energy. You put energy in, you get the same energy out. That's why we call them conservative forces. What makes a force conservative? There are lots of different definitions that different people will use for what makes a force conservative, but the simplest one is the one used in our textbook. If the force, or excuse me, not the force, if the work depends on the path you take in going from point A to point B, then it's non-conservative. If it only depends on the starting and ending points, then it is conservative. So an example here might be the frictional force. Chad's phone is sitting on his table, and if I push on his phone, I can push first to your right, then away from you, and move it from here to here. Now, in terms of the work done by friction, when I was moving it to your right, what direction was the force of friction? It was to your left. So, the force of friction was opposing the motion, so the force of friction was doing a negative work equal to The magnitude of the force of friction times the distance it moved. Now, when I was moving it toward me, what direction was the force of friction? Once again, opposed to the motion. And so I had work there that was the force of friction times that distance. So the total work was the total distance I traveled multiplied by the force of friction. Now, if instead of going in a square, I had just come diagonally, now my motion is this direction. What direction is the force of friction? Opposite. Still the negative work equal to the force of friction, which doesn't change as I go this, because it's force normal times coefficient of kinetic friction sliding. But it was a smaller distance. Because it was a smaller distance, there was less work required to move it diagonally than there was if I did the square. That's the definition of a non-conservative force. Another way to think about it is, I start here, if I take it around and come back to where I started, I had to do positive work on it the entire time. Friction was doing negative work on it the entire time. It didn't give back the energy I put in. My net work to get it back to the starting point wasn't zero. So we need to be able to identify the differences in the two. Now, to make life easy, gravitational force is conservative. It doesn't matter if I take Chad's phone, and I lift it straight up and then take it diagonal or horizontally, or if I just go diagonally. The work was only because I had gravity pushing down, and so it only depended on the vertical displacement. It didn't matter how much horizontal I did. There was no work involved there. So gravity is conservative. Electromagnetic force is conservative. A spring force is conservative. Other forces that we'll deal with are generally non-conservative. Things like drag force, air resistance, that's non-conservative. Frictional force, non-conservative. The force of my body pushing on something, non-conservative. I'm not going to get the energy back. I can't. If I did, I could go to the gym and pump iron. I do work on the iron to push it up. It does work on me coming back down, and I should have all my energy back. Wouldn't get tired out ever, right? No, I'm not that way. So the work I do is non-conservative. The work done by a motor or engine, those things are going to be non-conservative in nature. But gravity is conservative. So for conservative forces, we define the potential energy, and I mentioned this yesterday in lab. We define the potential energy by its change. Those three horizontal lines means is defined as. So this is the change in potential energy is defined as minus the work. And so as was written in the lab guide for yesterday, since the change in potential energy is defined as the work, then the actual potential energy could always have a constant offset. When we take gravitational work is the force of gravity dotted to delta x. And like I said, only vertical forces matter because force of gravity is vertical. And so that turns out to be mass times gravity times the change in vertical height. That's what the work done by gravity is. And there's a minus sign that I didn't write. That minus sign would be because as y goes up, the force of gravity is down, you'd have a negative work. So the work from gravity is minus mg delta y, which means that the change in potential energy for gravity, so I'm just going to put gravity here. So the change in potential energy for gravity is always mg delta y. And thus we say potential energy for gravity is mg times y, or h, since h means height. Height, y, vertical. So that's where we get this equation for potential energy due to gravity. Now an important question is, what is the reference point for this potential energy? Where is potential energy of gravity 0? And with gravity, because it has a linear relationship with height, it's quite convenient for us to say it's wherever I want it to be. And so we often will say, okay, I'm doing a problem and it starts up here and it ends down here. I'm simply going to say at this height down here, that's my height is 0. And so this height here, I'll just measure relative to that. And so the potential energy is 0 at a height of 0 since it's mgh. And up here, it's mass times gravity times whatever the difference is between these two heights. So with gravitational potential energy, it's up to you where you choose your reference point. And so, for instance, on part 3 of the lab yesterday, the reference point for gravity was such that your gravitational potential energies were all negative. And it made your total energy negative because of that reference point. Mathematically, physically, it's not a problem. It may be a little confusing because we want it to be a positive potential energy. Here's an example where it may be confusing, but it's really important to have it defined that way. We have planets orbiting the Earth, right? Orbiting the Earth, planets orbiting the Earth. I should speak better. We have planets orbiting the Sun. That one's accurate. These planets are orbiting the Sun, and they have gravitational potential energy, and they have kinetic energy. If the total energy, with our definition for gravitational potential energy, if we're using something not on the surface of the Earth, this equation here only works on the surface of the Earth where g is constant. If we have something that's not on the surface of the Earth, we have to use the potential energy for gravity is, and we worked this out yesterday in class for the calculus people, minus g mass 1 mass 2 over the separation. Looks just like the force equation, except for the force equation was over separation squared. This minus sign means that gravitational potential energy is always negative, never positive when you're using this form. And we set our reference point for this one when r is, as Chad told us yesterday, when r is infinitely far away, we set that to 0. So we always have a negative gravitational potential energy for planets orbiting the Sun. We have a positive kinetic energy 1/2 mv squared. That's always positive no matter what you do. When the total energy, which we define as adding the kinetic energy and the potential energy, if you want to be more precise, that's the total mechanical energy. When the total mechanical energy reaches 0, the planet is free to go. But if the total energy is less than 0, it's bound. Now, most of you are probably thinking, why would I care? We're not gaining or losing planets. But if, for instance, we're trying to send a satellite to go out of the solar system, we're going to have to give it enough kinetic energy so that its total energy is 0 or greater than 0. If it's 0, it just get out and free of us. If it's greater than 0, it'll actually still be moving when it gets very far away. Most of you are probably still thinking, big deal. I am not going to be working with that either. Well, we have atoms. Atoms have electrons orbiting the nucleus in paths that we don't know. We simply don't know. They're not doing circles. We can be pretty sure of that. But we don't know where they are. We don't know what paths they're doing. But we can calculate their energies. We can calculate their kinetic energy. We can calculate their electromagnetic potential energy. And if their total energy is less than 0, then the electron is going to be bound to the atom. So all of your bound state energies, when you look at the energy diagram for electrons in a hydrogen atom, you have the ground state energy is minus 13.6 electron volts. And then the next energy level is minus, whatever that is, divided by 4. And you have these different energy levels that go up closer to 0. And if you can transfer energy to that electron to bring its energy up to 0 or to a positive value, you ionize the atom. The electron has enough energy to become free of the atom. And so that's an area where, since a lot of you have taken a lot more chemistry than you have taken physics or intend to take physics, an area where you see that energy sign being an important thing. I only have 10 minutes left. I spent, 20 minutes on this slide, basically. This slide is showing a cuckoo clock. At the hour, this little door is going to open up, and a little bird is going to come out and go, cuckoo. And it's all cool. How does this clock work? It is powered by gravitational potential energy. When you want to wind up the clock, per se, you pull this string down. You just pull that down as illustrated in this picture. When you pull that down, you're doing work because that string goes up here and then has this pine cone hanging from it. And so the tension in the string is pulling up the pine cone. Assuming you go at constant speed, your work is going to be equal to the weight of that pine cone multiplied by the distance you pull the string. So you did work on it. But you did work against gravity. Gravity is a conservative force, so gravity is going to store that energy and give it back. So now the pine cone's up here and it's willing to give it back, and then the clock mechanism uses the gravitational potential energy to keep the clock going, and the pine cone very, very slowly falls. So, every day you have to go and pull that down so you have a day's worth of pine cone dropping to keep the clock going. So you can take how high you raise this and how much that pine cone weighs to calculate how much potential energy you're storing in gravity, how much potential energy it uses per day. I think it's a really innovative system, one that worked before we understand batteries, which are a lot easier for us to put a long-term amount of energy in than that. But it's very cool. And I don't know about you guys. When I was a kid, I always wondered, how did it work? Why do you have to why do you have to pull on things inside there to make, well, we had a grandfather clock, but to make it keep going. We was my grandmother. It doesn't work anymore. Sad. Okay, now my slide that has kinetic energy. Kinetic energy, the energy in motion. Here's a very standard kinetic energy problem. You have a roller coaster, starts at the top, comes down, goes through a dip, and then comes out at the end. This is a problem that we could have looked at earlier on, but it would have been really hard to solve. If you tried to solve and say, okay, what's the speed of the roller coaster at the end of the track, assuming no friction, before doing energy, all you would have had was said, okay, there's a force of gravity that's pushing down, and so when it starts going down the curve, that force of gravity is going to cause an acceleration. And we can use Newton's second law, use the angle, and calculate the acceleration, but then we'd have to continue doing that for every part of the track. So it'd be a pretty complicated calculus problem to try to figure out how fast the train is going at the end. But with work energy ideas, it's a very trivial problem. It's a very trivial problem because we have a relationship, the net work is equal to the change in kinetic energy. Now, instead of just solving this, I'm going to go to my next slide that has the steps to solving a problem. When you're solving a work energy problem, step number one, draw your diagram of the situation. Well, that was already done on the preceding slide. Step two, simply calculate the potential and kinetic energies at each location that's important in the problem. So the starting point, the ending point. Step three, determine if there are any non-conservative forces, for instance, friction. If there are non-conservative forces, you need to calculate the work done by the non-conservative forces. And then you use this form here of the work-energy relation. You haven't seen that form before. You might wonder, where does it come from? So it's like 3 steps. I originally put them in, decided to take them out and do it by hand. Work-energy relation was work net equals change in kinetic energy. We break the work up into 2 pieces. The work conservative and the work non-conservative. Give me an example of a conservative work. Work done by a spring, by gravity. So that's what is in the work conservative. What about the work non-conservative? Things like friction. Now, for work conservative, we had defined the change in potential energy was equal to minus the work conservative. So making that substitution then, minus change in potential energy plus work non-conservative equals change in kinetic energy. And finally, add change in potential energy to both sides. And you get work non-conservative is equal to change in kinetic energy plus change in potential energy. Right? It wasn't a big step. It's just restating the work-energy relation, but using our definition of potential energy. But it's really, really useful because now we can just take our physical situation and say how much non-conservative work was done. That's going to be equal to the change in kinetic and potential energies. One additional thing before I do a problem, we often will define the mechanical energy as the kinetic energy plus the potential energy. And so we often will then write this is equal to the change in the mechanical energy. Mechanical energy is the conservative energy. So mechanical energy is your potential energies defined for conservative forces plus your kinetic energy. Yes?
I didn't get everything on the last page. Could we just for a second?
I am going back to the last page.
Okay.
But I want to have the steps to solving the problem and then go back to it.
Okay.
So if we come back to here, if I want to solve something for, let's say, what is the speed at the end here, following my steps, the first thing I do is I have my figure. Boom, that's done. What was the second step?
Potential energy, kinetic energy at the beginning and or relative points.
Okay, so my kinetic energy initial. If I start from rest, what's my initial kinetic energy? 1/2 m times 0 squared is equal to 0. What about my potential energy initial? Okay, it's going to be mgh. And I have to decide right now where am I going to set my reference point for 0 height. And so I will randomly choose and. Where do you want to have 0 height in this problem?
The lowest point.
Okay, at the lowest point, so down here? Okay, so Ann chose that to be our 0 point, so this is going to be mass times gravity times, and I'm going to put the 25 meters here just so we're clear that that's what we chose. Now our final point is here, looking at the distances. This is at a height of 5 meters. So I would have potential, using the wrong symbol. Potential energy final would be mass times gravity times that 5 meters. And the kinetic energy final, 1/2 mass times the final speed squared that I'm looking for. So I've put my equations. Now, more generally, mg y initial and mg y final. Step 3, are there any non-conservative forces here? Not that we're using, we're assuming it's frictionless. It says the last line. If work done by friction is negligible. So that means no non-conservative forces, so we just have work non-conservative equals 0 then if there's no non-conservative forces. Final step, put them into our equation. So I have work non-conservative is equal to change in kinetic energy plus change in potential energy. That's equal to kinetic energy final minus kinetic energy initial plus potential energy final minus potential energy initial. Putting in my values, 0 equals 1/2 m v final squared minus 0 plus mg y final minus mg y initial. Once again, I went to using the y's instead of putting numbers in. I'm looking for v final, so just solve that for v final. Notice the m's are all going to cancel, right? Mass doesn't matter. And I'll have v final squared is equal to 2. I have to multiply everything by 2 times, there's a g here and a g here, so I'm going to factor out the g as well. 2g. If I move these across, this one becomes negative, so the y final becomes the negative. The y initial becomes positive when I put it across, so y initial minus y final. And so now I can put in my numbers. 2 times 9.80 meters per second squared times my y initial. It started at 25 meters minus my y final. It ended at 5 meters. And that gives me my speed squared. Do the square root and I have the speed. Of course, I will have a positive and a negative sign, but since I'm just doing speed, just the magnitude, I just take the positive sign. And so it's fairly simple to find the speed. We're actually out of time, so I won't go to my last slide, which was, well, I'll show you what it was just so you can appreciate. I was going to bring back a homework assignment that was not graded or a homework problem that was not graded, and show you how we do the parts B and C now that we have that. But we're out of time. So remember, there will be a Flip Friday for Friday. Do the worksheet beforehand.